Today, we're going to dive into embedded systems. My name is Marco Del Fiasco. While I give you a brief introduction of me, I invite you to scan the QR code in case you want to check the slides while I talk. So I'm an embedded system engineer. I'm passionate about music and electronics, so this was my natural choice to be an embedded engineer. I work as a contractor, mostly for audio, but I also had some experience with industrial and IoT projects. I've been working with DSP microcontrollers and system on chips, running bare metal, real-time operating system, and also Linux. In particular, today I'm here with my colleagues and friends from Elk Audio, where we develop an high-performance, low-latency operating system running Linux. So, the outline of this talk, I'll give you an introduction on audio embedded system, CPU and memory. We'll review some commonly used architectures for audio, coding for DSP, the OS, the choice of the OS, and then I will present you a case study. So I implemented an easy algorithm, an FIR filter, and I compared the results running it on 3 different platforms. So, of course, every embedded audio product is different, but they share a common set of ingredients. Like you will find an UI, a panel with buttons, encoders, display. Of course, you have all the audio I/O connectors. And then for digital audio products, you have a CPU connected to some codec, which does the analog to digital and digital to analog conversion. This is an example of a simple embedded product. It's a single board device. It has only one CPU doing the housekeeping and the signal processing. This one is a more complex product. It's a digital piano, where you normally have like several boards. Especially, you can have a CPU which resides on the panel, while the main CPU may reside on the main board, and it's used for the housekeeping, for rendering the machine logic, and optionally, you'll have also a DSP board. So the processor, in this case, the audio processor, is another CPU you have in the system. So this product is more complex in the sense that the CPUs have to communicate together, and there are many things that an embedded engineer need to solve. So the common design challenges. The customers will ask for features, the product needs features. So nowadays, having Bluetooth, Wi-Fi, good-looking GUI are some common requirements. We have to choose the right operating system and CPU type for each of the components. And then if we have a distributed system, we need to set up the inter-chip communication, handle the firmware upgrade. Distributed systems are more complex to handle. And then we have to face the debug and testability, which is very, very important nowadays. General rule, keep it simple. Simple is better. So if you're able to integrate in one CPU all the components, it's generally faster to implement and to maintain. But it's not always possible. The CPU and memory is an important part because you know that all the CPUs are different, all the architectures are different, and each of the architectures try to optimize some of the aspects. So all the CPUs execute instruction with a pipeline because it allows you to have an higher clock. Each instruction will require more cycles to complete. And there is this thing about the difference between latency and throughput. So what is the latency? The latency is the number of clock cycles required for the result of an instruction to be ready, while the throughput is the number of instructions per clock cycle that the CPU can fetch. So in this example, the latency is 5 cycles because the instruction needs 5 cycles to complete, while the throughput is 1. So every clock cycle, the CPU will fetch a new instruction. The execution in pipeline can have stalls. So in particular, when there are memory accesses that require more than 1 cycle, typically the entire pipeline will stall, and then it restarts again when the data is ready. There is one important aspect of the architecture that influences the performance of the machine. So it's the pipeline length. So typically, since it affects the instruction latency, it's critical for recursive algorithms. So if you're running IIR filters, the latency length might be a problem. Superscalar CPU. So the idea of superscalar CPUs is to fetch multiple instructions per clock cycles and deliver them to hardware units that are parts of the CPU, that are called like functional units, each with its own pipeline. So this architecture is quite common nowadays. The superscalar CPUs can execute instruction in order and out of order. So in order execution means that the CPUs keeps the ordering of the instructions that are written in the program memory, while with out of order execution, the CPU is free to speculatively execute instructions even if they are not needed, but then the results are ordered after execution. So this allows to maximize the occupation of the hardware units. Of course, the hardware logic is complex, especially with out-of-order execution. The important thing we have to remember is that the compiler is typically not aware of the underlying hardware. So the real-time optimization is done by the hardware itself, not by the compiler. Very long instruction word architectures are a little bit different, share the same concept of parallel hardware units, but this time they rely on the compiler and not the hardware. So the CPU has a simpler hardware, and the chip area can be used to do something else, like for implementing hardware accelerators, for example. So the compiler is aware of the underlying hardware, and basically all modern DSPs have a very long instruction word architecture, where it's typically very hard to write machine assembly code. Let me give you an example. So this is a very long instruction word processor from Texas Instruments. They have 2 sets of 4 functional units. So the programmer needs to tell to each instruction where it is executed. So the sub-instruction is executed in the S2 unit. And the programmer needs to know the architecture of the machine because it needs to know how many cycles each instruction requires. So it's very, very hard to write like this. Typically, you will use linear assembly, and you will run an optimizer after the assembly code. But nowadays, implementing straight in C is the most common and viable choice. Vector processing. So what's the difference between SISD and SIMD CPUs? So single instruction, single data are CPUs that execute the instruction only on one register, so one data, typically in our case of audio, a floating point value. While with SIMD, so you have single instruction, multiple data, the CPU execute the same instruction on an array of registers. So this will parallelize the operation and make the CPU run faster. Some examples of SIMD CPUs. So the Shark Plus has a vector of 2, so it can implement 2 parallel single precision floating point operations. The ARM Neon is 4, the Intel AVX2 is 8. There are multi-core CPUs nowadays of 2 types. The first one is the SMP, so the cores are of the same time, so they are homogeneous. They share the common address space, and there is one single operating system taking care of all the CPUs. So the operating system pins the tasks or interrupt to different CPUs according to its rules. With AMP, things are a little bit different. Here we have heterogeneous multi-core, typically, but it can also be homogeneous. With heterogeneous, you have different address space, and typically you are running different operating systems across the CPU islands. So an island is a group of CPUs of the same type. So you typically have Linux plus FreeRTOS, or you can have Linux plus bare metal. And the examples of AMP are having a CPU plus microcontroller or CPU plus DSP, or even microcontroller plus DSP. So there are a lot of choices when choosing a new hardware. The need for AMP. So the main reason for AMP processors is to offload the main OS for specific purposes. And in particular, sometimes it's easier like to write a firmware instead of a Linux driver plus user space stack to handle some system function. Not big, but a small problem maybe about AMP is that in the end, your software will have some vendor lockness with the particular chip you choose. But remember the importance of integration we discussed initially. So AMP is a solution. So there are those chips made of Linux-capable CPUs plus DSP or plus microcontroller that will allow you to integrate in the same device different functionalities with smaller space and easier development, I would say. This is about memory levels. So the CPU continuously loads and stores data to the main memory. If we want a large memory, we need to use the external memory, DDR memory, which is not fast. So the solution is to have like intermediate memories, which are faster, and use this layered memory level architecture. Some ballpark numbers. So the L1 memory, so the one that is closest to the CPU, is of one cycle typically. The level 2 could be 2 or more. If we have a level 3, it can be 20, 50. But if we are accessing DDR memory, it will cost like 100 of instruction, typically. One small clarification about this is that on system on chips, when we talk about L1, L2, L3, if any, we are talking about caches. So caches are memory that hold the content of the main memory to make the CPU access faster. While on DSP and microcontrollers, typically they can be configured as caches, but you are also free to use them as static memories. So this means that the programmer has control of where placing arrays of data. So if doing static allocation, typically you assign the most sensitive data to the level 1 memory because it's faster. But of course, it's smaller, so we need always to find some trade-off. If I have the cache, with cache, you typically have one problem. It's called cache trashing. So it happens when most of the cache lines are not in the cache. So they need to be fetched from the slower memory. This will generate jitter and instability because typically the cache behavior is random because there is your algorithm running on the CPU, but you also have other processes. So it's like random, and this will generate jitter. The access time of DDR is 100 times slower. So, if only one line of cache is missing, 100 cycles more or less in a processing frame is not so big. But what if you are missing 100 lines or even more? It depends on the algorithm. The causes of cache trashing are other processes running on the same or different CPU, even of low priority. This is very important. So you have your audio thread that wakes up, you process the data. Let's assume that the caches are hot, so we are very fast in processing. Now the audio task can sleep, and the CPU is able to schedule like other non-real-time tasks, maybe to the same CPU or maybe to other CPUs, but you have a shared cache. What if this program, in the time it can run, does a long mem clear operation or a memset? It will address a lot of cache lines, and the cache line will be full of unuseful data for the real-time task. So this will create a problem when the next audio period, the audio task needs to process data. The other cause can be low program or data locality. Or it's a badly written algorithm, but more typically is the data locality itself. So basically your data set is not cache friendly, or it's hard to make it cache friendly. I will share some facts with you that I learned. So having a shared memory path will make this problem worse, especially if you have shared level 2 memory, because different CPUs will compete with this resource. And where you have cache, you have always some amount of processing jitter instability, always. It depends on how big it is. But fortunately, there are some technologies like Intel CAT that might be used to make this problem smaller. This is an example of what processing jitter is. So in the second line, I have a GPIO that toggles when my audio thread is processing data. We see that the running period of the task is almost constant. We can tolerate, we can live with the jitter like this. But what if you have this? So the worst case execution time of this function is twice the average value. This is not far from the reality. I mean, so the problem with this is that when you have cache, you have to accept the fact that typically you need to measure and stay on the worst case, basically, because otherwise you'll hear audio clicks. This is not so uncommon. This is the same phenomenon with an histogram. So usually the algorithm will take 150 microseconds, but sometimes it reaches like 200. It's not twice in this case, but this is the distribution. So the y-axis is logarithmic. So typically, when you are handling with cache, my hint is to let it run for a big period, a big time, because maybe you might have one click every 1 hour if you are unlucky. Architectures for audio DSP. So what are the common choices? They are the DSP, the microcontroller, and the system on chip. Of course, there are a lot of specialized architectures, like DSP coprocessors, low-power DSPs, the XMOS chips, which is widely used in audio, which is an hybrid, microcontroller RISC processor. There are FPGA, ASICs, a lot of chips. But this talk wanted to address, the main used ones. So we will take a look at the first three. For the IIR filter testing, I used one DSP from analog devices, one microcontroller from NXP Semiconductors, which is a Cortex M7 processor. And for the system on chip, I used the Raspberry Pi, so it's a Cortex A72. Why a DSP? So typically, a DSP has an ultra-low latency, predictable timing, a relatively large amount of internal memories you can use to place your data. It can have hardware accelerator, which can be used to improve the performance. Usually, they require some low-level programming, especially if you're dealing with direct access to the DMA and the accelerators. And typically, with DSP, you need an external control CPU. It depends, but typically, this is how you'll manage a DSP. The first DSP was made actually for this product, because the CPU were not able to handle the processing power needed for this at the time. So yeah, they were invented basically to cope with architecture problems of the existing CPUs. And they are still there, so there is a reason for this. Some examples of DSP, so yeah, the famous Motorola 56K, nowadays analog devices, Shark, Texas Instruments, C6000s. The DSP reached the speed about 1 gigahertz recently. They also have multi-core, there are multi-core parts. This is the block diagram of the DSP I used for the IIR filter tests. So we see that it also has accelerators, even if in my test I didn't use the accelerators. You can see the core and some number of peripherals. So the key features of a DSP, taking this as an example, are audio-oriented peripherals, like you have clock generators, asynchronous tempo rate converter made with hardware, so with zero CPU overhead, and of course all of the SPDIF and audio port management hardware. There are general purpose peripherals like in a microcontroller, UART, I2C, SPI, timers, ADC converters for potentiometers. The internal memories are large enough, so 640 kilobyte L1 plus 1 megabyte level 2 memory. And as I mentioned, you have the accelerators. In this part, there is something missing, though. You don't have USB Ethernet display. This is the reason why, with this, probably you need an external microcontroller for doing other things. This one is the block diagram of the processor. So it's a super Harvard architecture. Probably it's what gives the names to this chip. It means that you have program and data memory that are separated. You have two tracks for the CPU, but it's super Harvard in the sense that you can, while you load the program memory with the instruction, you can still access two paths of data memory in the same clock cycle. So it's super Harvard. The buses are 64 bits wide, and it has 4 memory banks and an optional cache. So you might decide if using or not the cache. This is the core of the processor. So it is a very long instruction word. We see the arithmetic logic unit, the shifter, multiplier. They are different hardware units. It has a 11 stages pipeline, and it is a two-way SIMD. So it's a vector of 2. You see that the processor is like cut in half. So normally, since the instruction is executed only by half of the processor, while the other one is like idle. But if you enable SIMD mode, the same instruction is executed across both halves, and you double the throughput of the system. The internal memory. So the memory is divided in banks. So it's true that this allows parallel load and store from the hardware point of view, but what with us, with the programmers, so all the memory is not contiguous, so it's divided in banks. So we need to apply memory bank-aware programming. So we have the control, we need to decide where to put our data and code. Let's go to the microcontroller. So a microcontroller typically has a comprehensive set of peripheral and drivers. It's low cost. It will allow you some bill of material cost savings. They still have a decent amount of fast internal memory, low power consumption, and are suitable for low-end single-chip solutions, in my opinion. Some example, NXP IMXRT, the STM32 from ST Microelectronics. There are many, many others, of course. This is the block diagram of the processor we chose. So the main CPU is a Cortex-M7 with half a megabyte of tightly coupled memory. So the TCM in the ARM is like the level 1 memory, L1, so very fast, half a megabyte. It has a coprocessor, so an optional Cortex-M4 you can use for to offload the main core. And as you can see on the right, it has a relatively large number of peripherals. So this time you see the USB, the Ethernet, and so on. This is the pipeline of the Cortex-M7 processor. You might recognize it from the previous slides, superscalar architecture. So this pipeline is superscalar in order with 6 stages. There is support for SIMD instructions, but unfortunately, the Cortex-M7 is supports only vectors, so 8 bits and 16 bits. So for audio is not really attractive, this part. What about system on chip? So the system on chip typically offers an higher performance, an higher clock, and they are multi-core parts. It has a large peripheral set. It can have high-speed buses like PCI Express, where you can optionally connect some FPGA, so very high-speed stuff. The peripheral have an integration, so typically you have HDMI, you have a GPU inside the system on chip, and you can also have a neural processing unit. And they are suitable for high-end single-chip solutions. Some examples, NXP IMX8, 9, Texas Instruments AM62, and there are many chips from Rockchip, MediaTek, and many others. This is the Cortex-A72 core we have in the Raspberry Pi. So it's a quad-core processor. It's 128-bit neon SIMD. So it's the SIMD capability of the processor is to have 4 single precision words in the same executed in the same number of cycles as one. And it has a per-core level 1 memory, but a shared level 2. The pipeline this time is superscalar, 15 stages, but it's out of order. DSP coding and debugging. So there are some universal rules you may already know, but let's review them. So please avoid branches if possible in real-time audio code. Whenever you know the loop count, please tell the compiler or use templates. Some architectures require you to specify when there is no pointer aliasing. So this meaning your pointers will never overlap during the execution of the function. This is very important for some architectures. And then, of course, do not forget about the locality of your data, especially if you have a cache. So always try to be cache-friendly if possible. Software pipelining. So this is a loop optimization technique that many compilers use to optimize the loop. It consists of overlapping instructions from successive loop iterations. And we can jump to this. So the normal loop is 5 instructions long. If you don't apply pipelining, you need to wait for those instructions to complete and start the next loop. But if there is no data dependencies, your loop can be parallelized. So the compiler will try to schedule parallel executions of the loop, if it can, at the cost of a small prologue and epilogue. So you see that the compiler this way was able to save something, some cycle. But if this loop count is high, like 100, 200, or even more, things are going better. Loop vectorization and SIMD. So when the compiler is able to exploit the machine vector instructions, because typically they work under specific condition of data alignment. So the programmer usually needs to supply the pragmas. So every compiler is different, but as an embedded developer, typically you need to read the documentation and check out what are the conditions, try to respect them, and tell the compiler that those are met. So compiler role is very crucial for a very long instruction word and SIMD operation. It needs to assert that the conditions, certain conditions are true. And typically, what we need is to turn on the compiler feedback. So this is the GCC and the Shark as the same name option. So save temps will keep the assembly code there, but it will also add comments. And then our job is to compile our algorithm, read the compiler feedback, and try to adjust and iterate. This is how it typically works. This is just an example of compiler feedback. So we have a for loop. It was one iteration of the IIR filter. The compiler tells me that it executes the 2 iterations of the original loop in 2 cycles. So it's 1 Mach per cycle, actually. He used almost all the hardware resources, 100%. So very great optimization. Coding from SIMD. So if you wanted to use SIMD in a processor, typically you have to code like this and not like in the second form. This will make our code less human readable, but this is the only way to make SIMD work. So I also encourage you to watch this video. It's from my colleague and friend Gustav Andersson. It's an ADC video from the last year where it talks about this matter. So check it out, please. One thing to note about this SIMD, in my case it was a macro, so the optimal value might depend on your algorithm. So it's not 2 because the CPU is capable of a 2-way SIMD. Please keep this as a macro and try experiment, run the algorithm with the different values because it might change depending on the structure of the algorithm itself. Typical system optimization techniques for DSPs and microcontrollers. So memory placement, very, very important. Manual memory placement, basically. You need to assign critical code and data to the fastest memory and find the sweet spot, basically. And if you're running out of fast memory, things will get hard soon. So if your algorithm is data hungry, if you have a lot of data, then maybe the DSP and microcontroller are not the best choice. Then there are advanced techniques like overlay and cache freeze, but they are a little bit complex. What about Linux? So what can you do at the system level with Linux to optimize? The scheduling. Scheduling is the first problem. So you can use preempt_rt, a supervisor, or a dual kernel like Xenomai. I highlighted Xenomai because it's what I used in my tests. I used the Elk Audio OS in the Raspberry Pi. Then there are techniques for core isolation, tasks, and IRQ pinning. So basically, it's manually tailoring the OS. And if possible, try to use a CPU without a shared cache, if you have a system on chip, because it will have a cache, or use cache isolation. Debugging tools. So on this DSP microcontroller, you have IDEs, but GPIO probes, histograms, and the oscilloscope definitely will be your friend here. And you might have a serial console where to put messages. On Linux, with the system on chip, of course, you can work like with more advanced tools. You can use the system timer. You can use the file system to load the test vectors, store the data, and of course, you have GDB. Last part about the OS selection. So bare metal. This is the simplest example of bare metal system. So basically, we have the main function sets up the auto callback. So it will register an interrupt service routine typically with the DMA engine. Then the main task, will just loop on some control function. And periodically, your audio callback gets called, but is called in a different CPU mode. So it's in the interrupt mode. So typically, your audio callback is an interrupt service routine. This is the simplest way you can achieve like dual priority scheduling on an embedded system without an OS. Yeah, that's it. Real-time operating systems, they are used so you normally have the same services you have in high-level OS, but they are tailored for embedded systems. So they are lightweight and even more simple. Linux. What about Linux? So it's a full-feature software stack. You have stable and maintained API. You have system-level protection, virtually unlimited memory, and will allow you to have a higher level of abstraction from the underlying hardware. And then, of course, with Linux, you have tons of ready-to-use drivers and libraries. There are other combinations possible, but typically this is what you'll find out. So the DSP will use bare metal, a microcontroller will use a real-time operating system, and for a system on chip, since it's complex to handle, you'll have Linux typically. We reached the experimental part of this talk. So this is an FIR filter. Anyone here knows about the FIR filter. Maybe I can skip. So why I choose the FIR filter? Because it's inherently parallel. I am expecting high performance from SIMD, so from parallelizing the operations. And it will give me a feedback on the upper bound of the multiply accumulate operations per second that per cycle, that can I have from an architecture. And it will stress the memory and the arithmetic logic unit. Goals of the implementation, so easy and straightforward, no assembly, please. And I benchmarked the architecture, so I was doing only single core testing. This is a naive implementation of an FIR filters. It's the one you will find out on Google, basically. Very simple. I also implemented this one. So this, of course, is the same implementation, but now the circular buffer is rotated for every input sample. This time, you don't have a linear memory dot product, but you have the state. You see that it rotates modulo FIR sites. I expect this to work good because typically DSPs have circular buffer addressing in the hardware. So those are my two like FIR filter prototypes. Then I start implementing those variations using some common techniques. So on Shark, I started with restrict. I used the dual bank access. All aligned pragmas and loop count pragmas to inform the counter, the compiler about the conditions. And then I also use an accelerated FIR library that Analog Devices gives you with the code. So this is our naive version, optimized. You see I used restrict on the pointers, PM and DM qualifiers on the coefficient and state. So this means that the processor can access the memory in the same clock cycle because they are two separate memory banks and the pointer do not overlap. In every loop, I told the compiler everything is double word aligned and the loop count is minimum this count, maximum this, and always a multiple of this other number. And I did the same with the circular FIR. So you see the same techniques, so very lazy. This is the wrapping on of the Shark library function, nothing fancy. What the results are. So starting from our basic version, we reached like 0.5 Mach per cycle. My circular buffer implementation without any compiler pragma performed very well, like very bad, sorry, like 0.1 Mach per cycle. But after I optimized it, I reached the pink line. So I reached 1 Mach per cycle, which is quite good. But the Shark library definitely was the one who won the battle. So it reaches 2 Mach per cycles, which is the maximum throughput of the CPU. But it reaches this value only for very big FIR filter sizes. This is with 64 samples per buffer, so it's a little bit better, but basically the same results. On the microcontroller, so what I did there, so just some restrict keyword, I used pragmas, and I also tried to use an existing library. Results. So the basic implementation running from tightly coupled memory performed like 0.1 Mach per cycle. Yeah, all the other implementation are poor. The best I was able to do was the optimized the naive version that reaches 0.3 almost, and the CMCs, the ARM library, 0.5, about 0.5. Things are a little bit better with 64 buffer sample size, so slightly greater values. And on the Raspberry Pi, I did the same basically as the microcontroller because it's always GCC. Those were my results. So the best versions here is not the Cortex CMSIS DSP library, but it was my C version that was only unrolled and vectorized. So I reached a peak value of about 1.75 Mach per cycle. Greater values with 64 buffers sample size. So having a big buffer always give you a better results because, you know, remember the pipelining stuff, the overhead of the prologue and the epilogue of the software pipelining. Now I will do some comparison because I found which were the best implementations on all the architectures. I want to compare them on the real speed because the Shark and the microcontroller were running at 1 gigahertz, but the Raspberry Pi is faster actually, it's 1.5 gigahertz. So I'm showing you some data that now is normalized in Mach, so multiply accumulate operations per nanosecond, not per cycle, per nanosecond. And we will compare the best versions I have. Yeah, this is with 8 samples buffer size. So you see that the microcontroller has a stable behavior. I plotted the minimum average, and maximum here, because I want also to show you that when you run from internal memory, you don't have jitter. So the microcontroller is the blue one, reaches 0.5 Mach per cycle, but no jitter. The Shark reaches 2 without jitter. The Raspberry Pi, you see, you have to look at the worst case, so the lower red line. So after 256 steps, it starts to behave better than the Shark, basically. Otherwise, the Shark is better. This is with 64 samples buffer size. Things change a little bit. So we are almost always faster than the Shark here, with some jitter. But what if I have cache thrashing? So now I'm still using the Shark as a benchmark, so running from internal memory, and I simulated some cache thrashing by software with a simple function that spanned memory. And I also enabled the cache on the microcontroller. So now the microcontroller will jitter because it's using external memory for accessing the buffers. Here we go. So microcontroller has jitter. It's always below 0.5 Mach per nanosecond. The Shark is our benchmark. It's here, very stable. What about the Raspberry Pi? So with 8 samples buffer size, it's not so good. The jitter is very high, and a DSP is better here, much better. Increasing the sample buffer size, things change. And even with some amount of cache thrashing, with FIR filter size greater than 128 taps, it performs better than the Shark, and it reaches 3.5 Mach per nanosecond compared to 2. That's great. Last one, I will show you like comparing the naive version. So what if I'm a lazy programmer, I don't want to read the optimization manual, just I take the code from Google and run it. So those are the results with 8 samples per buffer. And things change with 64 for some reason. But please note the numbers. I mean, the Shark is 0.5, Raspberry Pi is 0.8. So it's almost 1/4 what we achieved by optimizing. So don't do this as an embedded programmer, please. Is this the final statement on the 3 architectures? Of course, no, because I tested only one simple algorithm. Recursive algorithms may behave differently because of the pipeline length, and the architectures are still evolving. So ARM has introduced Helium, which has, even on Cortex-M, so low-power microcontrollers, you have a vector of 4. So take a look at Cortex-M 55 and 85 parts. Shark is going to release an 8 SIMD. So it's 4 times more than the actual part numbers. With system on chips, they are always evolving. So they are pushing out the number of cores and the clock speed. So the race is still open. Some takeaways from this talk. So keep in mind your architecture, your parallelism, cache and memory size constraints. It's very important with embedded systems. And at the beginning, try out several implementations of your algorithm, because the architecture may help you just to write the code differently. Put some expectations on your CPU, then benchmark, monitor, optimize. And please stop optimizing by the 80-20 rule at a certain point. During my writing my code, I was trying to, can I give more? No. Stop, just stop. It's not always worth it. CPU selection criteria. If you need a few sample latency, no jitter, please use SDSP. High performance, multi-core, use a SOC. For simple and low-cost design, I will go with a microcontroller. If you want high levels of integration, you may consider an AMP processor, so like Linux plus DSP, Linux plus microcontroller CPU. It's very common nowadays. If you have a cache, please remember this inherent jitter and unpredictability. If going with DSP and microcontrollers, please double-check that your memory, internal memory, is enough to store code and data. Otherwise, it will get very hard. And probably going with a SOC is the best option. if you are tight on memory. Some other influencing factor for this choice of the CPU, the company background, internal team, of course, they play a role because, habits. Should we extend or make a better version of our previous architecture, or should we design a new one because we want to embrace the future, we're designing for the future? It's an hard choice. And yeah, I want to just put also attention to another topic, so younger minds. So what about the young developers? So are they more comfortable of learning to optimize code in a DSP on microcontroller, or just need abstraction and work on more powerful CPUs? This is also an open question. So we reached the end of this talk. This is my mail if you want to write. If you want to check out the Elk Audio OS for Linux, there is the link. And if you want to take a look at the code, I put the link for GitHub. Thank you.
We have time for